Okay. Okay. Well, hello everyone, and welcome to streaming Merkle Roots and Proofs in Clojure. I'm Mark Champine, one of the organizers of the Boston Clojure Meetup. So I'm going to start the presentation now, and we'll get this underway. All right. Okay. Can you see my screen?
Yep.
It's good.
Yep.
All right.
Looks good.
Okay, so I added a subtitle, which is the plus intro to blockchain. So that's mostly to give context to Merkle Roots and the specific use case that I've been most interested in. So hopefully there will be some interest in diving down into blockchain tech in general, and we'll see if we can answer any questions people have. So here's the agenda. I'm going to introduce my background here first. I have been doing Clojure for 13 years now. I can hardly believe it. I started out with version 0.09 when Clojure was really just a Java jar file. And the REPL was this, you'd run the jar and then you'd have to wrap the REPL with a decent line handling program. It's come a long way. So a few stats about the Boston Clojure group. So this started in January 2011. So Eric Coburn founded it. He eventually moved to Florida, and I became the primary organizer of the group in 2016. So about five years now, and we've had a pretty good run. For 4 of those years, we had our meetups in Kendall Square in Cambridge, and we've gone virtual since COVID hit. So one day we hope to get back to some live meetings. My professional background is as a security architect at Kronos and Akamai were my last couple of engagements, specifically web application security. And that was a good field to be in. The demand is still huge. There aren't nearly enough security professionals to meet the demand. But I decided 15 years of that was enough, and I dropped out of the working world, bought an RV, and traveled around the US for almost a year. And I was out there on the road when COVID hit. So far, I have not gotten the urge to go back to work yet. We'll see how it goes. So here's the rest of the agenda. I'm just going to talk briefly about how I got interested in this. We're going to explore Merkle Roots and Proofs, specifically, how they work, what they look like. We'll take a detour into blockchain, and then as a sort of a subtopic in Merkle Roots, there's this innovation in building Merkle Roots and Proofs from streaming sources. And we'll see why that's useful when we dig into that. But the heart of my exploration in terms of coding and so on was all around implementing an algorithm to do streaming Merkle Roots. So that was kind of fun. I'll show off, with a little live coding, how I implemented this stuff in Clojure, and we'll have a wrap up. And by the way, feel free to ask questions anytime. I'll do my best to answer them. But yeah, it's fine to go off and do subtopics as we go. Want to just have fun, keep this light. not dwell too much. There are parts that get kind of very down in the weeds, and I'm going to try to resist going too far in that direction. So, all right. So why did I do this? I wanted to learn more about blockchain and Bitcoin. Hopefully you are all in the same category and are interested in this this technology, so we can have some fun discussions. I found out that Merkle Roots and Proofs are generally useful. There are all kinds of applications that we'll see, in a bit. And of course, any chance I get to play with Clojure, I take it. So I have to, in full disclosure, say that I had personally one more motivation, which is that my son has a startup, and it is a distributed storage network that is based on blockchain tech. And so I wanted to understand, what they were building, how they were doing this stuff. And in particular, he really invented the algorithms for doing streaming Merkle Roots and Proofs. And I wanted to help, I wanted to review the paper and give him some feedback. And so that is where this deep dive came for me into streaming Merkle Roots and Proofs. Okay, so let's take a look at what they are. Just some background: patented by Ralph Merkle back in '79. One of their most important characteristics is that they have this log base 2 characteristic of efficient proofs, that an element is in a set without having to share the whole set. So anytime you can find log 2 effects, it can be tremendously powerful. And we have some of those in Clojure, in the form of trees and the persistent data structures. I think they're 32-way trees. And without that log 2 efficiency, we wouldn't have nearly the performance that Clojure has. Okay. So here's a depiction of a Merkle tree. It's a tree of hashes, a Merkle root. You can see here with the dashed line around it, these are roots. It's the top of any given tree. So you can see that there's actually a path of subtrees. There's a tree of 2. There's a tree of 4 leaves, right? And we work our way up to the root of the entire tree. And then, so the Merkle root essentially is a hash code that is unique to the entire set of leaves that it's built from. So if anything changes, if you reconstruct the root, you get a different one. That is, if any leaf changes, when you calculate the root, it changes as well. So it's a way of representing the integrity of all the nodes that it is built from. So a Merkle proof is a set of selected subroots. And you can see here in the dark blue which subroots would be part of a Merkle proof. The idea is, in this case, we're trying to prove that this hash of node K is part of this set of leaves, set of nodes. And so if we supply H of ij, this one, and this one, and then we have a known root then it's possible to reconstruct that root by hashing these values that are supplied in the proof with just a few additional hash calculations. So the way you would do that is hash the supplied node, the one that you're trying to prove, with its neighbor, and then hash that together with hij, which is part of the proof, to get this. This is supplied in the proof, so you can hash those together and get this. This is supplied in the proof, so you can hash these together and get the full root. So that just takes a very few number of hashes to achieve a calculation of the Merkle root. So I'm probably jumping forward a bit because we're going to dive into that a little bit more later. But this is, I think, a good representation of that nested or hierarchical tree structure. Go ahead, any question?
Yeah, so the values in the nodes are actually hashes of something?
Hashes of
Yes.
the children.
They're the
Yeah.
hashes of children.
Okay,
Combination
so
of, yeah.
So if you go down to the bottom like HK, what is the value of HK? It's a hash?
it's a hash. So
It's a hash of what?
So A through P, we can call them leaves, we can call them nodes. What they really are in general is just byte sequences. So
Okay.
yeah, exactly. So you feed a byte
Is this like
to the hash.
But they have to
Sorry?
be distinct. They have to be different. They have to be unique.
So the way I
Right.
think of it is the bottom row kind of doesn't matter. Like it could, like if you think of that as like the whole stretch from HA to HP, it could be like a Word document, right? And you're gonna take that Word document and split it up by paragraph or whatever. So, you know, the HK could literally be a paragraph from that Word document, or it could be a hash of that paragraph. It doesn't matter, right? So the idea being that as you go up, it's always the sum of what's below it. You know, so this could be for data integrity purposes. On blockchain, the bottom row ends up being typically hashes themselves, but it could be, to Mark's point, bytes or whatever.
Exactly. So
So
yeah,
you
these could be paragraphs. They could be, well, as we'll see in Bitcoin, they're actually spending transactions. But you can see that if there's any alteration, say in paragraph K, that if you were to calculate the hash, it would propagate, the change would propagate all the way up as you build towards the root. And so the root gets altered if there's any change to any leaf. Is that clear?
that makes sense. It's almost like you said, it's almost like a persistent data
Index.
storage thing where you just you redo the path for each one of those changes.
Right. Yeah, you know, it's
So effectively,
it's-
the bottom is seeded with just random whatever.
well, the bottom is whatever data it is that you are interested in, you know, validating the integrity of. Maybe it's, well, that,
Okay.
so if it's a contract, maybe these could be all paragraphs in a contract, and they're individually.
I see what you're saying.
And then once you build this tree on top of it, if anything changes, you will change the root by this
Yep.
algorithm. So you can tell immediately if it's like almost like a sign, right? A signing.
Right.
Yes.
And you
Yeah,
would
that-
also know which part has changed, right?
Well, no, not if you're just looking at the root, but
Right, yes, but you can
if-
trace it down, so you can say, you know, this has changed.
if you have the proof, right?
Right.
If you have these
You have
values.
the proof.
Exactly.
I always think of it as it's two parts, both related to the same thing, right? You're looking for log-to-n optimization for recalculating something, for recalculating the root when something underneath changes, or to have that log-to-n optimization when you want to do the proof, right? So this picture is a great example of that because I only need the blue nodes to do the proof. I don't need the entire tree. but I can basically validate that the root correlates to the new value of HK. Likewise, to recompute the root, I only need to recompute a log2n complexity. I don't need all HA through HP and rehash everything. I only need to go log2n up the tree to recompute the hash.
Yes, exactly right. So yeah, a naive way of checking the integrity of all these leaves on the bottom would be to simply to hash them all together, not hierarchically, but basically you could just concatenate them and calculate one hash over everything. And if anything changed, then that would change, your hash that's meant to verify that integrity. But then you have to do that work every time. You have to hash over all this data. And with this tree structure, if there's a change in any piece of this and you want to recalculate the root, you don't have to do it over everything. You just have to recalculate anything that is affected by its path towards the root. So that's where the log2 comes in. There's log2 of n hashes that are needed to recalculate a root after you already have.
So these leaves have to be ordered. Then they can't be a bag or a set, right? Because the ordering is important in knowing what the path is.
Absolutely true. Yep. Yeah, these are ordered. Okay, so we probably already jumped over a bunch of things, but let's see where we are. Okay, so this is just another depiction of what this Merkle root calculation looks like. In this case, this element in green is the one that we're trying to prove is a member of the set. And so these get hashed together. So yeah, you work up the tree, you build towards the root. And if you're constructing a proof that this is a member, you need to supply these three hashes. These are subroots. This is a leaf hash. You provide those. The root itself is something that's ordinarily supposed to be conveyed separately. It's a known value. And so that's the basis of your comparison. You have a root.
You're not storing the intermediate hashes then. You're just storing the Merkle root, and then you're understanding the path, the tree structure to get to the root, right?
Well, right. The validator will have access to the known root. And then when somebody wants to prove to that validator that this is a member of the set, what they do is supply 1, 2, 3 subhashes plus the leaf. They give that to the validator, and that's enough for them to reconstruct the root. Then they compare those values. If they match, then the membership of this is proven.
So why do you say the set? Because we just assert that it's not a set?
That was yeah, I misspoke.
Okay.
Not a set, a list essentially.
Okay, because I mean, you said earlier this could be used to search to see if something's a member of a set, or maybe I'm jumping ahead here, but I haven't seen the set yet.
Well, in the sense that the tree structure doesn't have to be ordered for these relationships to hold, right? So, and I think maybe the language is a little bit loose. We talk about this being a member of the set. What we have is, I mean, there is a set of elements over all the leaves, right? And there's membership in the set, but that doesn't mean that it is.
Right, because if I were to move one of those elements in a different order, that would change the root calculation, right? Because we assume that these aren't composable, like they aren't commutative, right?
That is correct.
Because that would indicate a change, right? So it's not really a
Yes.
set.
It's not really a set,
Okay.
except, I mean, so there's an additional constraint. It satisfies that it is a member of a set of leaves, right? When you
Well,
think
that
of
is
it that way.
specifically this section, right? Or this
Yes,
piece hasn't changed in
yes.
its location or its content, right? Because both of those are nailed down by
Right,
this
so-
calculation.
So the set membership is a weaker assertion.
It's more
so-
like identity, right? It's more is it immutable? You know, was it? Can we guarantee that it has not been modified? Is really the only guarantee we really have, which is valuable, right? But
Yeah.
I don't think it's a set. Yeah.
Okay. All right. So let's talk a little bit about applications here. So they are used in Bitcoin, and where it shows up is in Bitcoin's block header in the blockchain. So when a block in the Bitcoin blockchain has as sort of its primary reason for existence a number of spending transactions. You know, Joe paid Jane, Jane paid Charlie. And so a single block on the blockchain can have thousands of these transactions included in it. And in order to verify that a spend has already occurred and maybe prevent it from a respend happening, we need to know that a particular transaction was present. And so, as we said, this is a very efficient way of doing that. Now, you could just have a calculation over the entire set of spending transactions, you know, a flat structure, and calculate the root over that, but it would be less efficient. It would take more computational power. But the main thing is that, and we'll see this in a bit, when proofs are transmitted across the network, it allows you to send far, far less data to prove the presence of a transaction on a block than would otherwise be possible. The context in which this occurs is so-called thin nodes. So we'll see this in a bit also, that in a Bitcoin blockchain, there are many kinds of nodes. There are full nodes that have the entire blockchain, including all transactions. But there are also a large number of subsidiary nodes that don't want to expend the amount of resources that would be necessary to hold the whole blockchain. As you can see, recently, the Bitcoin blockchain is over 366 gigabytes. And so there's lots of devices that don't want to store and maintain that gigantic amount of memory or disk storage. So here's some stats. It says, based on log base 2, a typical proof without Merkle would cost about 75,000 bytes transmitted. And you can make that same proof with just 384 bytes to verify a blockchain transaction. If you're, again, at a thin node, one that doesn't store the entire blockchain, and yet needs to be able to verify to end users that a spend has occurred. All right. Let me pause there. Yeah, any questions about thin nodes and the blockchain? We're going to see the structure of the blockchain in a second. So, all right. Just a couple more uses before we go on. Merkle roots find use I was talking about the distributed storage network that's based on blockchain tech that my son's company runs. So it is built, this distributed storage network is built up of these autonomous hosts all over the world. And since it's a storage network and the people storing the data are being paid fees to store, right? It's sort of a rental, storage rental network. And so I, as a consumer, want to be able to know that they're not just pretending to store my information, that it's really there when I need it. And so Merkle proofs can also be used to not just, instead of say, showing that a transaction exists in a block, they can say that a file exists on a disk. So it's sort of that set membership again, that is, are you really storing this file? We don't want to make you calculate a root over the entire disk contents. So the way this works is that a probabilistic challenge is issued. It asks the storage nodes, I want you to supply a Merkle proof to me for file blocks 1, 7, and 25, and it generates these randomly. And then the storage host provides the proof, and once that's verified, then we can know statistically that that they are very likely storing all the files that they claim to be storing. So that keeps the hosts honest. Another use of Merkle is in certificate transparency. There was a famous, at least in the security world, breach of the worldwide public key infrastructure. It's called the DigiNotar Certificate Authority Compromise. And so after that breach occurred, they wanted to prevent this happening again. And the way they did it was by creating essentially a worldwide registry of issued certificates. So every time a legitimate certificate authority issues a cert, they send it to this this public record of all legitimate issued certs. And anytime somebody wants to check that a particular certificate is indeed one that was legitimately issued, they can ask for essentially a Merkle proof that that it was indeed on the list. And if it's not there, then you may have an illegitimate certificate and you should raise a red flag.
So Mark, a question about that.
Sure.
In that particular case, you know, the set concept sounds really valuable, but they would have to know like where it was in the chain, right? Of all the certs out there, they would have to know where it was located, because you can only test, is this still legitimate? You can't really do a search against the set this way, unless I'm not understanding this right.
No, I think that the Merkle proof that is supplied is enough to establish that it exists somewhere in the chain. The person asking for that proof doesn't have to supply an index or anything like that.
So it must be some natural order then, because we just confirmed that the ordering is part of the calculation. You can't do it without it. So something has to resolve in knowing where it is in relationship to the previous things. Is it time, or do you have to know like when it was issued, or it must be something that provides an ordering?
Good question. I don't know exactly how that works. We'll have
Would
to-
it be enough to know the hash of the thing you're looking for?
You got to do a search for. Well,
Yeah,
now you're
yeah.
doing a search against that,
Yeah,
right?
but
The
Um,
order of, I would describe it as the order of the things being hashed is established, but it's out of band to, to Merkle, right? So if you're looking at Bitcoin, going back to Mark's original pictures, the HA through HP or whatever it was would be like the order of spend transactions on the blockchain. And then the root would be the block hash for that set of transactions. So the order of those HA through HP was related to the order they were received by the validation node.
Yeah, that's
right?
certainly a blockchain. Yeah.
Right. If it was bytes in a Word document, it would be the order of the paragraph. So there's definitely an order to that bottom row, but the domain dictates what that order should be.
Right.
Yeah,
So in my question
right.
about the certs, there must be some domain, there must be something that places that cert in an order that then you can do the Merkle calculation. You can find that route, right? Or you can find that path.
I would
But you have
guess
to know.
it's probably like time from that CA is probably issuing the certs in an order, time ordered list, and that's how they compute the hash from or something like that, right? It's probably time
So
based.
yeah, it has to be on some
I
common
think that
clock.
might be an option.
It is
you're
absolutely
missing.
time ordered, yes.
What I was going to say is there not like an already established hierarchy of like top level domains? Like there's the ones that are just utterly top level, com or so on, but then you're going to have lower ones. So you just say, hey, this is the domain for this. So I'd look up the Merkle tree starting at .com and fall down to the subdomains to that. And each time you're assuming it's alphabetic. The issue I suppose would be you don't know if there isn't some domain AAAA.com ahead of you.
I don't know if they actually structure it hierarchically, to match the
Well,
essentially.
that's not the Merkle tree. That's doing the cert,
Right.
the membership.
So let's think of it this way. In order to reconstruct a root, you don't actually have to know the order of all the leaves. There's only a single hash that you have to provide.
But you have to know that in the next level up, you have to know what other hashes to include in the calculation to move up the tree, right? Which is why the ordering is nailed down. You have to know among all the ones that could possibly be over the 366 gigabytes, which ones contributed, which ones were my neighbor, right? In the
Right. So
order.
I assume there's an index and that they can essentially just look up its neighbor. And once you have its neighbor, the rest of the tree can be constructed from just the node supplied in the proof. So that I assume that's how it works. Okay. What other uses does this have? BitTorrent uses it to verify parts of a download. Git uses it to detect changes in the source tree. And there are quite a few NoSQL DBs that use it for replica coordination. So it does show up all over the place. Certainly Git is used by huge number of software developers worldwide. So you're using Merkle every day, whether you know it or not. So very useful pattern, definitely. Okay, so let's take this detour into blockchain. I don't know what the level of knowledge here is of blockchain within the audience, so we'll go fairly quickly over this. You can ask me to slow down if we're going over material everybody's familiar with. So first of all, as I mentioned, there are more than one kind of blockchain node. The Bitcoin blockchain, like many other blockchains, consists of essentially a network of computing nodes that communicate with each other, usually a gossip style network where if any node wants to share information with others, it transmits it out to neighbors, and eventually it propagates to every node within the system. The Bitcoin blockchain in particular has at least 3 kinds of nodes. I think there's even more. But there's three most well-known kinds of nodes. Full nodes store the entire blockchain. These light nodes only store the block headers. It's a tiny fraction of the full size of the blockchain. It's enough to answer questions about what kind of transactions exist, and communicate with full nodes really to do the heavy lifting. Then there are mining nodes. Mining nodes actually also have to be full nodes. What they're doing is creating new blocks to be added to the blockchain. And we're going to see in a minute how that is accomplished. So first, the blockchain structure. What does a block look like? It all starts with the Genesis block, the first block, block 1. With Bitcoin, this happened. Actually, I had just written it down. I don't remember when it happened, but after the Genesis block is created with no preceding block, second block is created like this. It has a hash of the block that precedes it, and some other data, timestamp, version. And here's the Merkle root hash that we have been discussing all along, which is the Merkle root over the transactions. These are the spending transactions that are occurring on the blockchain. And then we're going to see that this nonce gets heavy use in the mining process. So it's a chain because this hash of the previous block is included when you build a hash over this entire set of data and include it in the block that follows it. And so each is tied to the block that comes before by including a hash of that block. And then, as you can see, essentially, there's a ripple effect where any change in any of these blocks, if you wanted to recalculate the block, it would change the hash values. So, any alteration, any compromise in the blockchain then would be detectable, because it would essentially change all the downstream hash calculations and show where that corruption was introduced. So that's how these things are chained together.
So, Mark, a question: the timestamp, whose clock is the timestamp from?
Good question. I don't know if the timestamp is coordinated, on a, with some internode time system, or if it's just local time.
I mean, it doesn't really have to be in order for this to work, right?
In general,
I don't know. I think
the minor nodes are going to just kind of come up with their own blocks, so that they basically say, these are the set of transactions I recognize. This is the time I'm picking. This is my.
Yeah. So you can't guarantee it, because the clocks aren't a single clock.
Yeah.
So
What ends up happening is one miner gets voted by majority in the network to be accepted, and whatever the timestamp is in that block just becomes, the gospel.
Okay.
Yeah. The question is, what would be the effect if the timestamp was wrong? Would it have any?
Well, it can't.
Create problems in verification. I don't know.
It would have to be, proper order and stuff like that, or other nodes wouldn't accept the miner's suggestion. But yeah, could it lie by 3 seconds and no one would notice? Possibly.
Well, I'm just saying, because of drift. I mean, unless you have only one clock, one system assigning the clock timestamp,
Yeah,
you
you're gonna
can't
get skew.
guarantee that they're in order, right? I mean,
Absolutely.
the reality of that.
So it's not shown here, but I think there is a block index. So that's, I believe, what provides the monotonic ordering.
Right.
The timestamp, I don't think you can rely on these being strictly ordered.
From what I
Although,
understand, like
Actually-
each
actually, they would be
miner
ordered. Sorry.
each miner essentially gets to decide what the linear order is of the block transactions they receive. Like there is no overarching clock. It's just the miner says, in my time box, when I was king, I
Okay.
saw things in this order.
Right. Now, it's not like the timing is super critical because these tend to get issued only once every 10 minutes. But I think there's also an acceptance step, a verification step, where all the other nodes in the system decide whether they want to incorporate this new mine block.
That's right.
And if they find problems in the header that would disqualify it, they can reject it. So I assume that a bad timestamp would be one of those reasons for it failing the verification phase.
That's
I don't
what
know
you
the
call
I don't know the
bad, right?
details. But yeah.
Yeah, depends what you call bad, because you can't help the drift if they're coming from different clocks, right? You can't guarantee that they're not going to be in order and monotonically, you know. So I wonder, and I don't know, I just wonder how that's really used.
You can
Because unless
guarantee
you have
it.
one system doing the clock assignment, you're going to have that, right?
You can guarantee that they're in order if you reject any newly mined blocks that have out of order timestamps.
Right, but when I'm checking your timestamp that you made up with your clock with against my clock and what someone provides from a different clock, it's not going to go well, right? I mean, you're going to have
confrontational, but your
No,
clock
no.
doesn't matter. It's just the timestamp in the previous block.
Exactly.
Okay.
Yeah, it only has to be later
Than the
than the
last.
previous block's timestamp. It doesn't have to be in any order relative to your local clock. So
okay.
maybe they allow for some small amount of drift or skew. They would have to for this to work.
Yeah.
The
okay.
question is how big of a tolerance. It's something that probably gets decided over time and see what actually is practical. Okay, so that's the structure of a block and the connection between the blocks that chain them together. That makes a blockchain. So let's talk about mining. So mining is very, very high speed hashing. At least in practice, it's quite high speed. The essence of blockchains, reliable single view of a public record, relies on this idea that it's difficult in terms of computational resources to mine a block. And because it's expensive, because it's difficult, no one entity can have more than 50% of the total computational power of the entire network. And it's very important to avoid that situation because that compromises the blockchain's integrity. It essentially fails at that point. So, but because there's thousands of miners, maybe tens of thousands of miners worldwide, the possibility of anybody getting more than half of all that processing power is very remote. So, there's sort of an arms race in terms of hashing power. It started out, probably people just use CPUs, and then CPUs were too slow, and if you can mine faster, you can make more money. So mining moved to GPUs. That's why some of the video card manufacturers like NVIDIA have had explosive growth in their stock values and so on, and demand for the products, because GPU mining was very, very popular. But new kid on the block is ASIC miners. They leave GPUs in the dust. This is an example. This is actually a machine from my son's company. They had a subsidiary that made miners. So this guy can do 800 billion hashes per second. So that's a typical miner. You might see a mining farm with thousands and thousands of these in rows, all chewing up electricity. We have probably all heard the unfortunate characteristic of blockchain tech, that it uses lots of power in what seems to be a wasteful fashion. But there is value in the systems that they support. Okay, so when you mine a block, what does that mean? Success in mining is the discovery of a nonce. Remember, we talked about the nonce that's included in the blockchain header. You're trying to discover a nonce that, when included in a block and you hash the block, you get a hash value that's below a set target for the entire blockchain. So here's an example. Here in block 2, we have these hashes, and we can see that they have 4 leading zeros. So remember, it's unpredictable what the hash value will look like for a given set of data that you're hashing over. So it takes lots and lots of tries to change the data in a small way, which is to change that nonce, hash again, and eventually you do that enough time, by chance you're going to get a hash value that falls below a certain numeric threshold. So by controlling that threshold, you control how much effort it takes to mine a block. So you can think just probabilistically to come up with a hash that starts with 2 zeros is pretty easy. Every 4th block, just by chance, will have 2 leading zeros. And then likewise, we have 4 here, so 2 to the 4, 16, right? So every 16th block or every 16th hash attempt would satisfy the requirement of being below this threshold. So what goes into this hash calculation? As we said, we had the previous block hash to chain it to the block before. We have the Merkle root that is calculated over the spending transactions in memory. By the way, these spending transactions are occurring all over the network. And when a transaction occurs, it's broadcast to the full network. And anybody who's doing mining wants to incorporate transactions into the next block that they're going to mine, because essentially you get paid for incorporating those transactions. So they're watching all these new transactions flowing around the network. They collect a list of them. They calculate a hash of first the Merkle root and all those other elements of the header, and then they add a nonce. Essentially, this is just a number that gets incremented. Hash all that up and hope they get a hash result that falls below the difficulty target. I mean, it's actually below the value target. So the lower that target, the more difficult. So we hash the candidate block. If it's below the target, you win, you've mined a block. And if it's not below the target, you add one to the nonce and try again and again. And as we saw with that ASIC miner, you are trying, you're doing these hash calculations at 800 billion times per second. And it can take many hours, maybe even days of hashing at this rate to successfully mine a block, you know, at the difficulty rates that are set by the system. By the way, the difficulty is tuned every n blocks, and I forget the exact number, but say every 1,000 blocks, they adjust the difficulty rate in order, or the difficulty target, in order to keep block generation, that is the mining and adding of blocks to the chain, at roughly the same pace. And that's commonly once every 10 minutes. So worldwide, every 10 minutes, somebody wins the hashing lottery, comes up with a successful block, and can add it to the chain. And so if that starts happening too quickly, they recalculate a new target, make it harder, and then moving forward, the amount of time to mine the next block will increase. And they keep doing that, adjusting it back and forth to try to maintain that steady pace of blocks being added to the chain. Any questions on that?
Yeah, who are these gatekeepers?
They are anybody who wants to participate. So since you are paid for mining, that's the motivation. You set up a node, you run your miner, and that's essentially the nature of a decentralized system.
Yeah, but there's somebody who keeps fooling around with the target.
The target is actually calculated by the software that runs the nodes. But you know, you're right. The software that that governs all these things has to be created and has to be distributed. In order to participate in the blockchain, you don't have to use the distribution that is offered, you know, by whoever has created this blockchain. You could run your own software, but in practice, it's pretty difficult to try to create something this complex and participate in the blockchain.
It's because it's a consensus model, right? That others, I mean, if you introduce a hack and try it, it'll be rejected because the others won't share that. So your avenue to hack this is to get the majority of the big nodes to agree and to infect them all with your hack, right? Which is unlikely, but right. That would be the avenue yeah.
Maybe the best way to attack a blockchain would be to attack the source code of that.
Tell them all to update.
Right.
Honestly, the best way to attack a blockchain is to just target the users. They're usually the weakest link.
That's true. I mean,
like phishing, right?
Essentially, if you can get their keys, then you know you have carte blanche to spend and pay yourself from their stock of cryptocurrency. So in practice, that's the most common kind of hack, is these breaches of the wallets,
Yeah.
which sometimes are online. Go ahead.
I'm gonna say another thing I've often thought about is if you have loose collusion between nodes, say all the miners in a large group that are all hashing, and they say, hey, to the other group across the street, if our transactions are in a group, you'll always prioritize them over anyone else's, and we'll do the same for you. And so you don't have, essentially you have hidden constellations of miners that together prioritize each other's purposes. They can't necessarily corrupt the system because they can't gain a higher majority, but anytime the ball's in their court, they're the only one who gets to play.
Yeah, it doesn't have to be any individual who achieves more than 50% of the total hash rate. It could be any collusion between people. So if somebody wanted to make a mining cartel, get together with enough other miners to get 51% of the total hash rate, they could take over the chain. But of course, when that happens, essentially the chain fails and everybody loses. And so
if you know about it.
If you know about it, right? That's a good point. So and that would be an interesting question, which would be collusion detection, sort of like collision detection. But I'm sure there are techniques. This has been thought of. People have surprisingly, the blockchain system has withstood many attempts to subvert it, and it has been quite robust. I mean, there have been breaches, there have been failures, but it goes on, and they correct the problems, and so far it's still working. All right. All right, so let's talk about what happens after you win the mining lottery. You've successfully mined a block that meets the difficulty target. So upon success, you broadcast this new candidate block to everyone else in the network. The other nodes want to validate that block before they agree to add it to the chain. So there are quite a few validation criteria. A lot of it has to do with essentially the spending transactions making sense. You can't have an amount of cryptocurrency. If you split it into two pieces, the two pieces have to add up to no more than the original piece, things like that. So there's lots and lots of integrity checks, along with signatures. There's signatures on all these transactions, and those signatures are verified as part of the block acceptance. But there is, so the essence of this shared consensus is the idea of the longest chain. So you have people all over the blockchain trying to add nodes, and the chain that survives is the one that's longest. That is a rule that's kind of baked into the blockchain software. So this is the key to the consensus, because if you want to try to corrupt the blockchain, which you basically have to do is have enough mining power to add as many nodes, or to mine as many nodes as it would take to go as that deep in the blockchain. So if you want to corrupt a transaction that has occurred three nodes before the tail, the current tail, you'd actually have to mine all 3 blocks, and so that would actually take triple the amount of hashing power of the rest of the world, and they've already moved on because they accept the longest block. So that is the essence of the distributed consensus. All the nodes adopt the longest chain as valid. So what happens if you're successful in mining, you've transmitted it out to everyone, they decide it's valid, they add it to their copy of the blockchain and start sharing that around. You eventually get rewarded with fees for having mined that block. As part of the set of transactions that are included in that transaction set is one that pays the miner. And so once that's on the blockchain and enough more links in the chain have been added to make it very, very certain that it will be impossible to go back that far and corrupt the chain, then you get rewarded for doing that mining. And so you get paid in the cryptocurrency. That's the foundation of that blockchain. Any questions about mining, adding blocks to the chain, fees, and so on? Okay. Just in terms of what those transactions are, we've been talking really just about Bitcoin. Those are spending transactions, but really those things that are put onto the chain can be anything that is useful for for a group consensus. So, I mean, it could instead be, say, contracts, legal contracts between parties. Could be voting, as was mentioned earlier on. So, so the things that you put on the blockchain have the characteristic of being immutable and essentially the shared truth among everybody who participates in the network. So I just mentioned here, there are a lot of transactions that are added into the block because blocks are very expensive to mine, and we don't want any individual transaction to be very expensive to conduct. So that's why there's so many transactions in a block. Okay. So this is just a list of some of the things that are involved in the validation step. We're not going to spend too much time on this. I mentioned a few of these earlier, but I've mined a block, I've sent it out to everyone else. They're going to decide whether they want to add it to their copy of the chain. So they do all these things. Whoops. First, they make sure that the hash is below the target threshold. So you actually did enough work to justify this being added. There's something called UTXOs, unspent transaction outputs. And so you have to assure that the output of all the transactions is less than the input. So no money gets sort of invented out of thin air. You validate signatures on the transactions. And this Coinbase transaction is how miners are paid. It's the so-called block reward. So as I said, there's a special transaction that gets added to all the other transactions between people, and this special transaction essentially creates the cryptocurrency out of thin air, and that gets paid to the miner. So there's a bunch more things in the validation step, but you can find those online. All right, so now we're getting towards the interaction between Merkle proofs and blockchain. So let's just do an example spend here. Jane wants to pay 2,000th of a Bitcoin to Joe via transaction. Joe wants to find out if he did indeed get paid, maybe so he can decide whether to send some product that he's offering. The way he does that is to communicate with a thin node. There are a lot more thin nodes than full nodes, and they're nearby, for example. So it helps extend the reach of the blockchain network. So the way the Merkle proofs get involved here is Joe goes to the thin node and said, hey, did I get paid? And the thin node talks to the full node and asks, did the transaction make it onto the chain? And the full node says yes and proves it by providing a Merkle proof. The thin node verifies the Merkle proof with the hashes that are included in that proof, plus the known root, which is shared by all the nodes on the network. So if you validate the Merkle proof, then you can confidently say that, yes, that transaction did get incorporated onto the blockchain. You can feel confident in that and go ahead and release your product or whatever you're being paid for. Now, the deeper that that transaction gets within the chain, the more certainty you have in it. And so when it's the very last block, maybe you're okay with that for Bitcoin transactions of a certain dollar amount. But say you're doing $1 billion blockchain transaction, you might wait until that gets fairly deep, maybe 3 or 4 or 5 nodes get or links get added to the chain, which makes it extremely secure. So the deeper it goes, the more nodes nor blocks that get added after the block containing your transaction, the more confidence you can have that it is impossible to revert. So, okay.
So Mark, what would be what would be a situation in which not waiting that long, like, would make you less confident? Like, what would happen that would undo something? I thought that couldn't be done once it's in the calculation in the chain. It's locked in, right? Because of everything coming after it. I guess just one thing after it's all that matters, right?
Well, if you remember, since this is decentralized and nodes are adding new blocks all the time, there can actually be situations where there's a very close timing between the node that was successfully mined by one miner and one that was mined by another miner, and then you have 2 different parts of the network that receive that block, verify it as good, add it to the blockchain, and now you actually have what is in essence a fork. You have two equally valid chains that have been constructed by different parts of the network. And so to resolve that, the process continues until one of those chains grows longer than the other. And once that happens, everybody adopts the longest chain.
So it's eventual consistency in that sense. And
is
does any
eventual.
miner know what, at any point in time, what is considered irrevocable and what isn't? What is subject to being bumped?
As I said, it's purely sort of a rule of thumb that confidence in the into the certainty of that transaction being included in the blockchain goes up as more nodes, as it gets deeper, in the chain. And you sort of have to make your own decision about your level of comfort. It's very, very difficult. I've never seen anything wait more than three deep. And so it takes about a half an hour for 3 new nodes to be added to the blockchain, 3 new blocks to be added to the blockchain, that is. And at that point, it's so rock solid, it virtually never, would happen that some other chain incorporating all those, but longer, I should say, another chain, longer chain with an entirely different set of blocks could be adopted because, again, because of the computational power needed to add blocks. And so remember, you have tens of thousands of these miners working to add blocks simultaneously all over the network. And so there's just, as we said, without some form of collusion, the likelihood of anybody getting a substantial percentage of the overall mining capacity is very remote. So that's basically, did that answer?
Well, I just know, there's lots of consensus algorithms, right, used for like distributed databases and such. And I guess I was just under the assumption that your typical, and I don't know the details of these algorithms, but it's under the assumption that at some point there's something where you're in a known state, you're in a known irrevocable state, right? And it sounds like that's not true here, right?
It's not true here, no.
Okay.
Right. So you sort of have to rely on the difficulty that it would take to essentially overpower all the other miners in the world. Mm-hmm. And again, that goes up very, very substantially with every additional block on the chain. So, all right.
Mark, we are at 8 p.m. Eastern now, so I'm wondering if we should take a little bit of a break, and it's fine either way. I just want to see what the sense is.
Anybody want a quick break? I guess we already have somebody stepping away. So yeah, why don't we take 5 minutes and we'll come back, and I'll try to pick up the pace a little because we still have a lot to do. Oh, okay. So, or we can take a vote. Anybody else? You want to continue on, or you want to take 5 minutes? Anybody want to speak up?
I'm good to roll.
I think 5 minutes would be good.
Okay.
With the objects.
All right, let's take 5. Okay, we're back from the break, and now we are ready to move on to this subtopic of Merkle Roots and Proofs, which is streaming roots and proofs. This is where we get down into the weeds. So first of all, as I mentioned, there's a worldwide distributed storage network. This is, you might call it Airbnb for disk storage or something. It allows people who want storage and are willing to pay for it, and people who have storage and are willing to rent it out to others, to make contracts, and those contracts are stored on the blockchain. We talked about contracts before, right? Which is one application of this public ledger. So the streaming Merkle Roots and Proofs were developed to facilitate some of the features of this distributed storage network. So what does it do? It lets, the proofs allow the nodes in the SIA network check that the data stored by the hosts is still there. You don't want to rent out a terabyte of storage to other people and you're being paid whatever, $5 a month to store their data. You go to actually retrieve it one day and you find out that they've been lying to you all along. So yeah, this mechanism essentially just keeps people storing the data honest through these challenges. And the challenges take the form of Merkle proofs. Now, with an ordinary Merkle root and Merkle proof, you load all of the leaf data into memory in order to create or validate the proof. This is a classic way of building a root would be to divide the number of leaves in half and recursively join them until you have a complete root. So you divide it in half, you divide it in half again and again, and then unroll that, and you would get a full root. So all those leaves have to be in memory, at least when you create the initial set of hashes over them. So a streaming proof lets you essentially process a stream of nodes that are sent to you over the network and construct the Merkle root or proof essentially on the fly without storing all of that data that's being incorporated into the proof. So that saves a lot of storage space, and it especially since these are taking place on tens of thousands of individual nodes, some of which that don't have a ton of processing power. So it saves quite a bit. The algorithm was explored in a paper. Here it's where it's published. If anybody wants to actually read the original paper, it builds on the concept of something called a binary numeral tree, which the definition is a set of perfect binary subtrees called eigentrees that are recursively joined into a single tree. And that's kind of what I was describing as a typical approach to building a Merkle root, this recursive joining. So the observation in this case is that these subtrees of a given size correspond to bits in the binary representation of the number of nodes or the position of a node within the tree, depending if we're talking about constructing a root or a proof. So we'll see an example in a bit, but as you can imagine, since a tree of say of four, say you have 4 leaves, and each pair of those is hashed together, and then each of those 2 is hashed together, you get a tree. Those 4 original those 4 leaves form essentially, it's always a 2 to the n chunk of leaves that are part of the stream that you're calculating over. So let's just to review this again. This is the relationship as you build a Merkle tree up from the leaves. Okay, so terminology wise, this would be considered an eigenroot over an eigentree because it's a perfect 2 to the n sized list of leaves. And so you can see that there would be a natural correspondence with the bit pattern in an index or a node, a count of the leaves being hashed over to create a Merkle root. So here's an example. So say we have 11 leaves that we're going to create a root for. So look at the bit pattern of the number 11, right? 1 0 1 1. So the place value of each of these in binary, right? This most significant 1 bit has the value of 8. This has the value of 4. This has the value, 2 and 1. So if we look at a construction of a Merkle root for 11 nodes, we can see this correspondence. You see how there's 8 nodes that all get hashed together to a single eigenroot, and that corresponds with this 1 bit, essentially at the 4th index, index 3. So 2 to the 3 is 8. We have 8. So what this is going to come down to is looking at the number of leaves that you're going to build the root from, looking at that pattern, and using that to decide how many. So remember, these are coming in a stream, say starting from left to right, index 0, 1, 2, 3, 4. These are coming to you in a stream. So say you know that you need an eigentree of the first 8 leaves. So you can read 8 of those from the stream and construct a root over them. And now you have that root hash, and you can throw away the 8 leaves. You don't have to remember them. You don't have to store them in any way. You're done with them. So this bit pattern tells you essentially how many leaves to take off this stream, construct a root on, and then move on to the next one, right? So we see here, if you have 11, you have a bit pattern of 1 0 1 1, which is binary 11. If we add 1, we have 12. And now you can see that we get a very different set of eigenroots. There's only 2 of them here. we have one that represents 8 and one that represents 4 of the leaves. So 1, 1, 0, 0 is 12. Here's our eigentree with an eigenroot representing 8 leaves, and here's one for 4. So you basically build up your tree in this fashion, looking at the bit pattern, hashing them together, and then doing that repeatedly until you've consumed all the leaves in the stream. Once you've built this structure, there's one there. This is an eigenroot, another eigenroot, and a leaf. You can hash all them together to get the root. So this is essentially used for both the root and the proof construction.
So Mark, if I understand that right, if you look at the top, right, I only need to calculate. I only need to get to the 1, 1, 0, right, as the first significant digits of my binary, because the whole right branch is encoded as a function of the left branch and the root. So you don't have to actually go and fetch any of that content that's coming from the right branch, because you have stored the root. You just have
Correct.
to reconstruct the left branch so that now I can say, without consuming the whole file, if it's a file, like for example, I don't have to read the rest of those blocks, because I have enough to know that if it's changed, it won't add up, right?
Exactly right. Yeah. So for example, this set of 8 leaves represented by a single eigenroot, as long as the leaf we're interested in isn't within that tree anywhere, we know that will never change. We never have to recalculate that. We can simply use that to represent everything in that portion of the tree.
Mm-hmm.
And so we only have to do rehashing and calculation of anything that is within the path from the leaf of interest up to the root. So yeah, exactly right.
You only have to store n log n or so leaves in memory at a time, plus whatever the space their hashes take up.
Right. Yep. Log n. Is it n log n? I think it's just log n.
Yeah,
Okay.
n log n is like a habit. Just n.
Yeah.
Just the height, the depth of the tree, right?
So here's a couple more examples. In this case, so I took this right from the paper. We actually have to read from left to right. The least significant bit in this case is on the left. This was really to show sort of visually the correspondence between these eigentrees and the bits within the index. So, so for a proof in which we're only interested in a single leaf, we do it in this way. So let's just do the middle one here, which is, so you can see these are all the same set of leaves, right? And we want to prove that this leaf, this leaf is present within our list of nodes to be included in the root calculation. So so we read from right to left for the 1 bits and left to right for the 0 bits, and use that to build up the entire tree. In this case, we encounter the 1. So let's see. So that's 4 here, because this is in, remember, we're counting this as the least significant. So that's worth 1, 2, and 4, right? So reading right to left we consume 4 nodes and construct an eigenroot. We read 2 more nodes, construct an eigenroot. And then since we've exhausted all the ones, we are now at the index of the leaf to be proven. All right. So now we start from the other direction. 2 to the 0 is 1. So we read 1 leaf from the stream and construct its eigenroot. And then this represents 8, right? Because we're reading again, lowest to highest significant. Now, there aren't 8 leaves left in our stream, so we simply consume the rest of the stream that exists, and then build the root from that. So here's the eigenroot from the remaining leaves in that stream. So that's it. That's how we build the structure up from a stream without being able to see or have available all of the leaves ahead of time. So again, the proof are the set of subroots. So 1, 2, 3 subroots plus the leaf. We can hash that all together and get a root value and compare that to the known root. So this is where we're kind of diving into the weeds. I don't want to spend too much time on it because you can always go to the paper if you want to work through the algorithm. But I just thought it's sort of interesting to see that that there is this technique that allows you to construct the roots without storing all the leaves, the roots and the proofs. Oh, so this is the one we just did. Sorry, I put it on its own slide so you can see how that works. The ones subtrees occur before the leaf to be proven, and the zeros subtrees are after the leaf to be proven. And those all are included in the proof. So that's it. I was going to go to the code now and just take a look at how I implemented this. Any questions on the streaming style of proof construction? I am focusing only on single leaf proofs. There are more advanced forms for ranges and a selection of roots that are all built on this same foundational principle, but that's an exercise for the reader. Okay, so let's look at Clojure finally. Since this is a Boston Clojure meetup, got to have some Clojure. This is online at my GitHub site. I created an API that really just has 3 main elements. There's a function to create a root given a stream of nodes or leaves. There's an API to construct a proof from a stream, and the index of the leaf that we're trying to prove is a member of that list. And a verify function, which you give it a proof and a leaf and the known root, and it will come back and tell you whether its reconstruction of the root matches the one that was supplied as, out of band as the known correct root. Just a few notes on the implementation. Since you're working extensively with byte arrays, and they're fairly large byte arrays, they kind of make a mess of your REPL when they're printed out. So I created an override for Clojure's print method that would take a byte array and encode it in a more compact, readable fashion. So that was kind of fun. Whenever I would do a print line or a PRN on a byte array, it would give me the pretty shortened, readable version of it instead of showing me the large array of individual values. So could come in handy for anybody who's working with big byte arrays. My code wasn't meant to be the most Clojure-like. It was really intended to follow the pseudocode in the paper as closely as possible. This question came up before. What are these transactions? What are these blocks or leaves or nodes that we're talking about? So in my test code, I just use single-digit strings as my nodes, but the code doesn't care what is passed into the hashing function. It could be a megabyte, and it would just be as happy. So if you wanted to try to create, for example, a Merkle root over all the transactions, spending transactions for Bitcoin, you would simply need to represent those spending transactions as a stream of bytes, somehow, up to you, and work just as well. And so I included a trigger warning here. In order to sort of force the code to deal with the streams as a stream, and not say as a lazy sequence, for example, I created a wrapper around the file which presents a stateful stream interface. So we'll see it read a few bytes, and then we come back later and we read a few more, or I should say blocks, read a few more blocks from the stream. In the Clojure world, since we have immutability, it would be the same stream every time you read from it. But in our case, every time you go back to the stream, essentially you get whatever is remaining in the stream. So that was sort of to force me to implement this stuff in more of a not in a Clojure fashion, but staying true to the limitations of the algorithm. So just show my correspondence between the pseudocode in the paper and the Clojure code that I came up with to represent it. You can see that it follows pretty closely. There's an insert where we're taking chunks of leaves from that input stream and building up this structure incrementally. So I'm using a map, and the original code uses an array, but it essentially serves the same purpose. The finalize step, we talked about doing a fold over all the eigen roots plus the leaf. And so in my case, I just implemented a right fold and pass it in all the values to be folded together. and it essentially does a reduce, but it's a fold right. A reduce is a left fold. And the root calculation, I just reduce over all the inserts of leaves that are being pulled from the stream, and then run finalize over it, and that is a root calculation. So let's go to the code. All right, I'm gonna share Emacs. Okay, can you see my Emacs buffer? I'm not sure what everybody else sees. Good to go. All right.
Looks good.
So, so I have a routine to just calculate a hash over any byte stream. So I'm passing in strings and then using get bytes to turn it into a byte stream. So when I said earlier that it works on any stream of bytes, it wasn't quite right. It actually would work on any string that represents a stream of bytes, but it would be easily adaptable. So a parent hash, this is when you're working your way up the tree. You have already hashed 2 leaves, and now you want to create a hash of hashes. It concatenates them and hashes the result of the concatenation. So that's a parent hash. Here's the fold that I was talking about, which I implemented simply as a reduce that calls the arguments in the other order on the reverse of the collection. So can sort of show how that operates here. Show call shows what it looks like, what the calling sequence looks like of a function that's passed in. So I'm going to create a version of that where the function is the word hash. So when I do a regular reduce over range of 4, 0, 1, 2, 3, it first hashes the first 2, then creates a hash of that with the next one in the list, then creates a hash of all that with the next one in the list. But a fold right does it in a different sequence, right? It hashes the last 2 things on a list, and then a hash of the element prior to that, and then repeats that until it has a single root hash. So here's that insert function that we saw earlier. Every time we get a new node to insert, we take a parent hash of what was previously at that height in the tree with the node. We increment the index value and then put that into the tree. The dissociator gets rid of what was there before and replaces it with a parent hash. So these inserts are akin to counting, really. You know how when you're repeatedly adding in binary, how there's a carry operation. Well, when these parent hashes occur, they essentially are carries, right? So this association is between sort of the level of the root the height of the root and the hash that is at that height. So if you hashtag, there are 8 elements. 2 to the 3 is 8. So that's a height of 3. You know, that tree, that recursive tree has a height of 3. So the structure that's built in maintains the current hash at a given height in the tree. And then here's my finalize. So if we want to create a root, we're going to insert all the leaves in the stream with a reduce and then call finalize. And so let's give that a shot. So I'm going to create a fake block stream, which is simply, let's see, you can see it here. These are my blocks. And now we're going to create a Merkle root over that stream of blocks or leaves. And now what you're going to see is, whoops, sorry. Yeah. So that's what a byte array looks like without the override of the print method. So if we fix that, now when we calculate the root, it displays that root hash with a nice string rather than long list of byte values. Okay, so that's roots. So let's look at now, excuse me. The construction of a proof. So here's how I build Merkle proofs. This limit function is essentially how I implemented that stateful read. And what it does is we'll read at most n lines. If you don't have that many left, it will give you the remainder of the stream. Here's a couple of functions that deal with that manipulation of the bit pattern. Remember, we're looking at that index. We saw if there's 11 nodes, there's a bit pattern for 11. So I have routines that essentially give you the bit positions of the ones in that pattern versus the bit positions of the zeros in that pattern. And now we have a function that constructs a proof. So what this is doing is it takes all the ones, it essentially follows that algorithm that we did by hand. It looks at the ones in the index value and then creates a subroot from the input stream of length k. So that's what the subroot function does. It builds a subroot of a given size. So it's going to do that for all the ones in the index. then it reads the leaf. And then it constructs subroots for all the remainder leaves in the stream. And that is your proof. So that's a set of leaves. This is the leaf to be proven. And then the set of eigenroots or subroots that are that come after the index. So here's an example. You can see the output there. We get one subroot at height 2. We get a subroot at height 0 previous to the leaf. And then after the leaf, we get a subroot height 1 and height 3. So this gets passed to the verifier. Here's a utility function. And another utility function which can construct a root from a proof and a leaf. So we're going to call that with this verify leaf function, which simply takes the known root and compares it to the root constructed from the proof and the leaf. And so we're going to run through that. This is a known root. Call it known root 12 over all the leaves in my 12 element set of blocks. We're going to create a root from that leaf to be verified and the proof that we constructed. And there's the verification roof. And so we can see that if we pass in this leaf that was used in the construction of the proof and the proof itself, and we call the verify function, that comes out correct. Now, if, say, the leaf was corrupted, or we're past the wrong leaf and we try to do a verify on it, we get a failure of the verification. So now we know that that node or leaf 5 was indeed in the original set of transactions or nodes or leaves, whatever you want to call them. So that's it. That's the code. It's really very, very, very simple, small amount of code. But one of the hardest aspects was, well, first of all, every bit must be exactly right, or the entire thing breaks. So anything is out of order, anything off by a single bit makes the whole thing blow up. And then coming up with these, essentially an algorithm to loop through all the ones and building all the subroots before and after the leaf. That was the interesting part. So that's it. Now you have Clojure code for doing Merkle roots and proofs. That's my demo. Any questions? Hopefully it was straightforward enough. And again, all the code's online. It's easy to essentially read through it all and work through the examples in, probably 20 minutes. So very accessible.
Cool. would be really nice to add visualization to it. That might be our next
Oh,
meetup.
yeah, that would be neat, I guess, if you would see the subtrees as they're being built up.
Mhm.
I think the thing to visualize would be, yeah, the structure as it's being constructed by inserts. So you would see, here's the structure. Now we add one more node. We see that ripple by creating eigenroots higher and higher in the structure. That would be neat. I should look at how that might be done.
John,
Maybe
that
with,
might be a transition to your talk next month.
oh boy.
Yeah,
Visualization of this thing.
Yeah, trees and grass are a little more tricky, but yeah.
Yeah, I mean, there are graph libraries that will do graph visualizations. So it might be possible. Food for thought, anyway. Go ahead.
Yeah. I mean, I saw this thing today by the Wolfram guys. It was like, oh my gosh, like, what are the rest of us even doing? It was all on graphs. Very, very fancy stuff.
Yeah. Stephen Wolfram, I'm halfway through his talk for Reclosure, so I'm looking
I was
forward to
thinking I
seeing
need
that.
to go watch those talks.
Yeah, I think they're all up on YouTube now. There's a Reclosure channel on YouTube that has collected all the talks. They might not be broken down into individual talks yet. I think there was like a day 1 video of 8 or 10 hours and a day
You're
2.
telling me we just have the root video and we have to figure out the leaves?
Yeah.
If someone has a link to that, it'd be great to post that in the chat or something. Or
Oh yeah. I can.
It's definitely
find
in the
that.
tulip stuff, but
So let's just finish this up and then we can stop the recording. Just want to mention that there are a whole lot of topics that we did not cover today. It's a huge space. You can get a PhD in blockchain easily. So here's some things that were part of my learning journey as I was trying to understand the entire ecosystem. What is a crypto wallet? And there's various incarnations of those. A cold wallet is something that's entirely offline. It's just a bit of data in a file. There are online wallets that participate essentially as nodes in the system and can do verification and transaction and so on. There's this concept of seeds. There's a deterministic process for generating all the public keys that you're going to be used in your spending transaction. So that's a whole interesting process of how a set of keys can be generated from a seed. A lot of topics around spending, validating, more about block rewards, fees. Oh, mining pools. I've actually done some mining myself with the machine you saw earlier.
An ASIC?
People, sorry?
With the machine you saw earlier, are you referring to the ASIC?
Yes, yeah, exactly. The ASIC, the 800 gigabyte per second miner. People generally don't set up their own nodes. It's a lot of work, a lot of resources. So you can join a mining pool where your mining effort is grouped together with dozens or hundreds of other people, all mining together as a team. It's one of those forms of collusion we were talking about, really, except that these pools are not large enough to threaten the integrity of the blockchain. And basically what happens is you all agree to share in the profits of of the pool. So everybody's mining away, and one of the miners within the pool scores a block, and the reward for that gets distributed among all the people who are mining, who are part of that mining pool, prorated based on the amount of effort that you can demonstrate that you expended in doing that mining work. So
Micropayments, huh?
yeah.
It averages out the swinginess.
So right, over time, it averages out to reflect the true contribution, the true amount of proof of work that you're performing. And there's some online stuff that talks all about the SIA distributed storage network, how it works, and some of these details around its use of Merkle proofs and roots, and a lot more. I relied on this site called Learn Me a Bitcoin, and I would recommend that to anybody who's interested in blockchain tech. It dives way down into the weeds, into the very nitty-gritty details of these topics that I'm listing above. Wallets, how they work, key generation, signing and validating, and especially the blockchain itself. This is all around the Bitcoin blockchain specifically, but it explains the protocols that are used for communication between nodes of various kinds, and dives very deep on how, especially how new blocks are constructed, and all the parts that go into it, and sort of the whole ecosystem around spending transactions, which is a whole subject in itself. So what I found out was that this, the whole system, the whole Bitcoin system, is really insanely complex, and I'm just baffled that the whole thing works, but it does. There's a whole bunch of features that were part of the original Bitcoin paper that introduced Bitcoin to the world, some of which have not survived today. They've found out that it didn't really work right, and so there have been tweaks to the software, but a lot of it is held up. But yeah, Learn Me a Bitcoin. Great resource, very clear writing, very clear explanations. So, one other thing I learned was that the founder, the creator of Bitcoin, is somebody that is not known. There's an identity which is Satoshi Nakamoto, but it can't be traced to an actual human. This is a pseudonym, it's an online name. Nobody knows who he is, if it is indeed a he. But when he created the this Genesis block and kicked off the whole system, he rewarded himself with a large number of Bitcoins, and whoever this person is worth, I believe, about $80 billion in Bitcoin. So there's one of the richest people in the world has an unknown identity because of essentially the anonymity that blockchain, that Bitcoin provides.
The issue, of course, is if Nakamoto ever wanted to sell out, then it's like, oh no, the creator is selling out, and that will cause the value to crash.
Yeah, definitely. And I think with enough spending transactions, you wind up de-anonymizing yourself So,
I think he's just embarrassed that he lost his wallet.
oh, I actually have a little bit of a story about that. My son's co-founder paid for his undergrad schooling with Bitcoin speculation. He bought it when it was cheap and it went way up in value. But along the way, he had a wallet that had a very, very long password on it, and it contained several Bitcoins. And the password was very long and not written down anywhere. He had committed it to memory. You can see where this is going. But one day he tried to unlock his wallet and was unable to do so, and tried brute forcing it. He thought he knew most of it, and so he would try small permutations on what he thought was the password. But after quite significant effort, he gave it up for lost. And so the Bitcoin sitting in that wallet is lost to the world forever, and lost to him specifically, very sadly, because it's probably, I believe it's worth somewhere over $400,000 now. So, ouch. Hopefully he'll get all that back by growing Skynet to take over the world and send a Terminator robot back to the past and all that. I'm sorry, Skynet is the commercial side of the SIA distributed storage network. So anyway, that's my crypto tragedy story. Okay.
It would be interesting to do a study on this sort of thing. So I have stories of forgetting my passwords or other similar things. And often it correlates to me switching languages. The password could be numeric, or like the code could be numeric. And I completely forget it if I'm speaking a different language for an extended period of time.
Yeah, it's the sounds that wear a groove in your memory, the sounds,
Yep.
not the
Yep.
digits, right?
Yeah, and I have a story of how I couldn't use my bank card in Russia because I had no way of contacting the bank from there, and I completely spaced out the PIN. And I came back and was able to do it. So I think there's something really interesting in like how people remember passwords and what context you have to get
memory.
back. Yeah, you have to get back in the right context, and then it comes back to you. But if you're not in the right context, you can do whatever you want. Nothing helps.
Yeah, I'd say my own password story was I was in Mexico and lost my phone, and just the stress of the situation made the friend I was with forget his phone password. So we became simultaneously lost and or locked out of both our devices at the same time. Well, off in a foreign country.
So it's also related to foreign language, and it's contagious. Great.
I'd say it was more stress rather than the foreign language.
Yeah.
I was the one speaking Spanish. He just got stressed and couldn't remember. The other interesting thing was a gestural password. The final interesting thing about passwords that I recall is there was some interesting stuff about subconscious passwords. Essentially, you'd play a game and the computer would judge essentially whether you had played the game before.
See, maybe we should stop the recording here before anybody confesses anything too compromising.
Yes. Well, I was carefully thinking of what I was going to mention. Okay, I'm stopping the recording.